All right, so how's it going so far? Still nobody? Check the book. You're missing a lot. You're really missing a lot. You know that, where's Andrew? He's not here. Andrew is doing fantastic job. He's converting any book into audio. He's making his own LLM. It's open source on GitHub. He got like 1,000 stars. It's really getting great attention from the community. So many people tend to use it. And you should be the first one to use it, actually. So please reach out to him. Try to use his own tool. It's very useful. You can use it while driving to school. So just convert any book into audio. Enjoy it as it's something nice. So you can use it for a chapter or section. Before coming here, you can just listen to that particular section. And probably you'll get something useful out of it. The nice thing about the book, it will give you the story. So it starts from the history, who invented that method, why they invented, what kind of issues they had in the past, and so on. To give you some context, rather than understanding discrete topics, so you'll be able to connect them together. And this is something nice, especially when someone asks you why we are doing this, why this is useful, right? We're studying computer science, but why we're trying to do a lot of Boolean equation? This is not math class. So all of those kind of crazy questions, you will understand them better from the book, not from classes. During our undergrads, we used to have many books. So you go to the library, we see different books. We go to online, we see much better resources than classroom and so on. And we used to check all of them for particular topics, especially when it's hard, really, it's difficult to understand. We try to check different authors. Sometimes they have different mindset. Some of them like prefer to reflect it to real example, like cartoon example or real life example and so on. So you might understand this topic in a much nicer way. And then you have different questions, different answers. So it's really good to check all these resources. Believe me, as I said last time, currently you have a lot of free time. Really, whatever you are busy in it, 3 years later, you'll realize that, oh, I was much not busy as in now. As you move on with life, you start building your career, start focusing on job, focusing on your house, family, wife, kids. So things will get exponentially growing, right? So take this opportunity to grow now. Now, just focus hard on your study and your degree. Try to get something out of it. And you'll see like it really pays off after 10 years or so. It's never get wasted. Even how you get skills to present in a classroom. If you want to be a teacher, for example, you're going to teach. You understand the material and you're going to explain it and so on, but then one of the students asks you, I didn't get it. Doesn't make sense that you repeat the exact same thing because he already didn't understand the first time. If you repeat it the second time, probably the same thing. Third time, the exact same thing. You need to really change your way directly. You tell them more examples, more things. Oh, how about you think about it from different perspective? And how you get that skills? By practicing, getting different opinion, attending conferences, attending YouTube videos, and so on. Okay. Even I used to watch lectures of other professors explaining the exact same topic. Sometimes they have something nice, like it could be a slide, it could be a way to present, it could be animation, it could be anything like that, right? And directly when I saw those, I got inspired. Okay, how about using the exact same thing in my slides? You give them still credit, or you could come up with your own animation, own things based on what you saw so far. And this is how you keep improving. So even after I post the slides somewhere on iCollege and so on, it could be like after 1 week, 2 weeks, I change them locally on my machine. I don't change in iCollege, of course, doesn't make sense because need to be synchronized with the recording. But at least I keep improving. And this is same for even our lab research talk, our presentation. Whenever any guests coming to our lab, for example, we present something about our research, and those slides normally we keep updating them every 2-3 weeks, adding new material, new stuff. And this is how you improve yourself. Don't ever like just get the bare minimum and said, no, this is enough, done, move on. This is a very bad way of improving yourself, building your skills, getting much better, or at least getting the bare minimum to compete with the market. Once you graduate, you'll see a lot of very strong candidates out there, not from this university only, but from many other great universities. So be ready for that. All right. I'm still waiting the TA to give me the grades for all the things passed so far. So once I get them, I'll send you those alerts. I think the deadline in this week or so to submit the alerts. We're currently in this book. Hopefully we'll be done with chapter 2 by today. And chapter 2 is extremely important. And it's really fundamental to all other chapters. So once we move to the processor, to the caches, to the DRAM, you'll see that all those things that we saw so far are extremely important. And that will be the conclusion of the second project assignment, which is about how you translate a truth table into an equation that the processor can execute. Okay, this is an extremely important, as well as this project assignment will rely on the first project assignment, which is converting the decimal into binary numbers. So make sure you get the things correct and working. Even after you submit, you might still discuss it with Gemini, with ChatGPT, with Claude, with anything you like. Make sure you get the things really correct all the time. All right? So we're still in the compute stack, in the logic layer, which is extremely important layer where we do all the calculation in terms of transistor level. Although we simplify the view, we don't see the transistor, but we see a gates. And gates is abstraction view of the transistor. So every gate is built on top of a couple of transistors, as we saw in lecture 4, I guess, where we implement the NOT using 2 transistors, for example, right? We implement the NAND using 4 transistors, and so on. So each of those gates is really abstraction view of those transistors. Right? Probably by this slide, you already get the idea of how we can convert the logic into gates. Whenever we have an equation, how you convert it into a set of connected gates. And we'll see a brief example over here. So if I ask you to convert this into a circuit, can someone draw it for me? Let's try the blue or the green, maybe. The green for the first time. Can someone help me to draw the circuit? Want to convert this into a circuit that has input and output. Maybe on board here. On board. Draw the circuit. Where? Good question. I want you to experience my suffer. Choose the way you like. Excellent. He starts from the input. Yeah, please, everyone follow.
Professor,
Amazing. Excellent. Excellent. Great job. So why you draw it the way like that? Why you didn't start with the or, for example, or something else?
Well, so my logic was like the OR is made up of those two inputs, which come from different AND gates.
Excellent.
Or, I mean, you know, otherwise you could. No, it's probably.
So remember, is this product of sum or sum of product? Sum of products. What does it mean?
Multiplication plus.
Excellent. So this is a summation equation that has multiple terms, and those terms are adds up. So all of them, we add them up. So how many terms do we have here?
Five inputs to actual.
Yeah, so we have two terms over here, right? And we have 5 literals or variables, right? So where are the terms? This one, right? And the other side. And they have add sign or addition sign, right? And then, so we split those two into 2 sides, and we start working on each of those sides separately. So on the first side, we said there is an AND operation or multiplication between them. So he drew the AND sign over there, and then we see a NOT gate on B only, which is a bar over there. So we try to flip B into this way. Then we have the A, we have the AND. We are done with the first term. Now with the second term, exact same story. We have a multiplication sign between 3 variables, C, D, E. So he chose to have 3 input gate, single gate with 3 input. It's up to you. If we have a restriction in the question and we ask you to use only 2 input gates, it means only 2 input to any of those gates, regardless whatever this gate is. Now, if this is the question and this is the restriction, then we cannot use this way. We cannot assume 3 input gate. And then we need to split them into 2 gates. So if this is AND, we would draw it first. We consider 2 input. It's up to you to choose which of these 2. It could be C, D. It could be also D and E. It could be C and E. So if we go with the same order, we could go with the C and D, but the C has a bar on it. So we need to negate the input. And it's up to you. Either you add a bubble over there to indicate that this is inverted, or you could add a NOT gate over there. This is the NOT. Then we could have it over there. It's exactly the same thing. Now we are done with the first 2 inputs. We take the output into another AND, and then the third input would be E, and that input or output goes to the OR gate. Okay? So this using 3 input gate, this using 2 input gate only. So it's up to the question. Sometimes we don't have these 3 input gates. We only have 2 input gates, so we cannot use this one. So consider everything here canceled, including this wire. And then you can consider this view to replace this 3 input gate. All right? And then the OR, because this is sum of product, then we end up having an OR gate at the output. Right? That's excellent. So this what would look like. Remember, never flip the gate. Never flip the schematic drawing. Okay, so always start from the input to the left side, the output to the right side, and then start from left to the right. Start building gradually your circuit from the input all the way to the output. Okay, don't get confused. So here are some recommendations. Inputs on the left side, outputs to the right side, gates flow from left to right. Straight wires are better, but sometimes we cannot have all the time straight wires, so don't have it leaning toward the gate. don't make this, for example, straight line from this gate to gate. It's a bit hard, so sometimes you need to detour the wire, but make it all the time 90 degrees or vertical, okay? So for example, if you want to connect a gate over here, or a gate over there, do not cross it like that. Just make it vertical, try to have all the time 90 degrees, okay? Sometimes it's a bit difficult for you, especially if the circuit is getting heavier or thicker or with more gates, and then you don't have space to add too much wires. So you can use one of these 3 tricks. We always prefer what we call as a T-junction. T-junction. What it means, if you need another wire, for example, if you have another gate over here at this side, and you need this gate to connect with this circuit, with this gate, how you would connect it? I want to connect the AND, the output of AND, to this gate, whatever this gate is. Ideally, or maybe I can ask someone. Let's see how you think. Any volunteer? Any volunteer? Yes, please. Try again. I want to connect the AND to this gate. Let's see. Just a wire. Excellent. Excellent. How do you know this?
I recalled we were able to split off the output.
Excellent. Excellent. That's really great. So remember, we want to take all the time 90 degrees wire connection, right? So don't ever make it like this way. Just try random drawing. Don't do that. And whenever we want to cross another wire, it's up to you. You could cross it straight, or you could make this arc or curve over there. And that indicates that there is no connection over there. Okay, so it's up to you. In 3 ways, all of them are correct. You could cross it directly. It still means there is no connection. Okay, even if they are crossing each other, doesn't mean they are connected to each other. So the green and the red here are not connected. And then you could do the same thing over here. Or you could simply make a jump, half bubble. And that indicates the same thing, that we are jumping or leaping over the other wire to avoid it, and then continue with the same path.
Professor,
Yes.
can you turn the camera? I can't see anything.
Which camera? We have 2 cameras.
The one where you're writing on the board. Thank you.
Hopefully it's clear now. Can you see it?
Yes, I can see it.
All right, thanks, Adan. Yeah. So now someone could ask, like, if you want to connect this red with the green, what should we do? So we said if we cross it this way, then we are not connecting them together. Then if we want to connect them together, what should we do? We have a trick over there. Wires connect at a dot. And it means if whenever we want to cross wires and want to connect them together, then just add that little solid bubble. It means there is a connection over there. Okay? So we have this wire going straight, and we have another wire over here. This again doesn't mean there is a connection. They are not connected, right? If we add a dot over there, then it means both wires are connected together. Okay? This is extremely important in order to have a clear schematic of any circuit that you'd like to explain. Okay? Yes, please.
Just to clarify, so, and maybe this is me remembering wrong, we're not supposed to connect wires like that from the output, right?
Excellent, excellent. Don't ever connect two outputs together. We already explained this, right, in the past. So this is extremely wrong, right? Because if the two output having different values, then the wire will pick which value. We have 1 and 0, 1 over here, 0 from here. We cannot connect those together. But we can connect one of the output to an input of a gate, for example. So we could pick like this output. We can connect it to an unlimited number of inputs, for example. That's fine. And this way you can add a dot over there if you want so. In this case, it's optional because we are not avoiding these wires because that's the only source for those. So it's up to you to add these dots. Or you could ignore them. But in this case, it's legal to connect the output of one gate as input of many other gates. We already explained this, right? Excellent point. Don't connect two outputs together. This is not allowed, right? But at least you got the point how we could cross two wires together without making a connection. Right? Any question? Okay. Now, we want to draw the circuit that's represented by this equation. Assume like you hand this equation to a company to implement it for you, and then you ask them, can you build this circuit for me? What they would do. First, you would ask yourself, is this sum of products or products of sum? Sum of products. Excellent. It means that this is a summation equation, and we have multiple terms added together, right? And each term has a multiplication in it, or AND gates, right? As simple as that. So how many terms we have over here? 3. Want to try? Want to try draw it? Yeah. Which color you would choose? All right. Want to use this side? Excellent. You start from the left side, from the input. I'm going to build the first term. I have 3 variables, 3 literals. This is first AND gate. I think the lid has a razor. If you want to use it. Excellent. That are 2 bubbles because we have 2 nuts, and the third one is also with a nut. Excellent. All right, now we are done with the first term. Now the second term. Excellent. You see how he is crossing the wires without making any connection, as we explained in the previous slide. If you want to connect them together, you add a dot. But if you don't add a dot, it means they are not connected. Now we have A without a nut, and then B with a nut, and then C. Amazing. And then we are done with the second term. We're going with the third term. That's the third AND gate. We got A without nut. And then B with a nut. Amazing. This is what I'm looking for. I really want this drawing to be very complex so that this will be a nice motivation for the next slide. Let's see how we can solve this cumbersome connections. What is this gate should be? Yes, excellent. Yeah, this is how we draw it. The previous one is wrong. What is the output? Excellent, excellent, amazing. Thank you so much. Any question about how we draw it? Yes, please.
So, I understand all the main thing is it better to just have it all as one in a sense instead of PVC?
Have it as a one means?
As in like breaking the 1A into 3 separate lines.
Oh, I see. Because normally you have this as a switch, single switch. If you add it as 3 A's, then that's 3 switches. And you might mistakenly enable one of them, leaving the other untouched. And then you're not having A, you're having something else. If you guarantee that all of them will be the same value, then yeah, you could split them. But if you split them, you need really to make sure all the time you assign the same value to 3 wires. But in this case, it's much better because you just assign value over here and it will be distributed directly to all wires. Okay? So if you split those as separate input, it will be confusing because they might have different values than the A over here. Okay? Now, but this is extremely valid point, how we would solve that. For example, how many NOT gates we would have here? Let's count them. 1, 2, 3, 4, 5, 6, right? That's one issue. So here, how many A bar do we have? 1. How many B bar? 3. But all of them are the same, right? So we have A bar, we have B bar. Do we have C bar? Yes. Then there are 3 nuts, in fact. But over here, we have 6 of them. So why we add 3 extra? That's the first thing. Second, do you see those wires? It's really difficult for you to track. The more you add wires, especially look at this. We have really here 3 connection or 4. 1, 2, 3, 4. So we have 4 connection. Now, which is which? It's really difficult. Yes. Yeah. Excellent. Excellent point. What do you mean by iteration?
Instead of like having multiple copies.
Yeah. Because you want to guarantee that every time you change the value of A, it propagates to all of them, right? If you make multiple copies of it, then it will be difficult. Okay, I assign to A at the top as 1, but then I might forget the A in the middle to assign it also as 1. And then the A at the bottom, the same story, right? But over here, just assign a value of 1, and then it propagates through the wires. Done. And this is, in fact, how we have it in hardware. So there's a single switch called A. You enable it, done. It will send 1 to all those wires. All right. Now, remember this, or maybe let's keep it. I need it to compare. And now let's switch to the other board. Let's see another way how we could represent this complex circuit using a simpler way. And we could respect the exact same value of NOT gates. We said here we only need 3 gates, 3 NOT gates. Over here, we needed 6 gates. Okay? Let's see. How many inputs do we have in total? 3. Excellent. So we just draw vertical wire. I thought this is new. It says premium. I paid maybe $4 extra to get premium. Okay, this is A. A, B, and C. Done? This is the first step. We have 3 inputs, 3 wires, right? Now let's make a copy of it. And now let's add a NOT gate, a NOT gate. You remember how we draw it? Triangle with a bubble at the end, and this is the output of it. We make a copy over here. And what we call this? A bar. Okay? Now, let's add a NOT gate over there, a NOT gate over there, triangle with a bubble, then we make another wire. What do you call those? This is B bar, this is C bar. Perfect? Okay. Done the easy step. Now let's go with the gates. How many gates do we need? Assuming you don't have any restriction on number of input to any of the gates, we're not requiring you to use 2 input gates, for example. So it's up to you. You want to use 3 input, 4 input, doesn't matter. How many AND we have? This is 1. Hopefully you can see from this side. 2, 3. Okay. Now, the first one, what do we need? Maybe look here better. All of them NOT. So one A, B, and C. Okay, it's easy for us. We can take from A bar, B bar, C bar. Done. The second one, B and C are NOT. So we take from A, this is A. You cross like that. And then one of the NOT, one of the black ones. Now this is optional if you want to add a dot over there. Okay? Now the third one, the B is NOT, so we go with the blues. We go with the first blue. B is NOT, so we go with the black. And then we go with the other blue. And then we could add our dots. Why it's optional in this case to add the dot? Because remember, if those wires are crossing, doesn't mean they are connected, right? We agree on this. If this crossing this wire, they are not connected, not connected, not connected, not connected, not connected. Only at this point they are connected. So they are not crossing the wire really, but in fact they are going through the wire. Okay? Likewise in here, likewise in there. And then now, as simple as that, just add. Hopefully, then can you see it?
I can see.
Perfect. Now just remember, keep it all the time vertical. Don't lean these wires, 90 degrees, and then you connect. And over here, you have the one. How is it? Which one better? Right side or left side? Right side. Now for this one, it doesn't matter how complex it could get. You could add 3, we call this, by the way, 2-level circuit, because we have 1 level vertically as a gate, and then another level, okay? So this is 2-level circuit. Over here, 1, 2, we only look at the gates, don't look at the wires. 1 level of gates, another level of gates. So 2-level. If it is 5, 10 level, doesn't matter. This way always work best. The only downside is that you need to have these long wires and you cannot detour. You always go horizontally with the wire with the gate. So if the gates get, the first level get really long number of gates, then you should expand those wires, which is not a problem, right? You still have space in your paper. Any question? Now, if we count, how many NOT gate do we have in here? 1, 2, 3. These are just a wire, okay, taking the same value. Remember, we have the output, single output, going to N input, which is allowed. There's no problem with that. Okay, don't connect output with another output. That's not allowed. How many NOT gates do we have here? 6, which is expensive. You need to buy more gates from the market. Here is cheaper. You just need more wires, which is the same case over here. You need wires still, right? Good? Okay. So if I ask you to draw these, please all the time use this method. Unless it's really simple circuit, like 3 gates, 2 gates, then it doesn't make sense to propagate. Remember, if the circuit does not use any NOT gate, you could eliminate those gates. You could eliminate those gates and their wires. Okay, you don't need them. If the circuit does not use any NOT at all in the equation, really no need to add those NOT gates. Okay? The goal here is to allow to reuse the NOT gate as many times as possible. That's why we allow them to have here, because we already know that all terms we are going to use. All right. So this slide, I don't like try to remember or try to make a rule for this circuit. So it's better to understand how it works, and then it's easy for you to apply it for any scenario. But just as a matter of fact, whenever we talk about sum of products, then it's always drawn as AND gates followed by OR gates. I don't like this way of explaining it, but it's really much better if you understand what you are doing, and then you will get this structure really easy from the equation itself. Because we said sum of products mean the terms are added together, right? And each term, there's a multiplication in it. So you would know that there is an AND gate followed by OR gate, because you need the summation of all those terms. When we look at the product of sums, then there are terms, and you are making a product out of all of them. It means there is an AND gate between the terms. And we look at the term, when we call it product of sums, it means each term, there's an addition happening inside. So that's why we will have OR gates, because to build the sum, and then followed by AND gates, right? Now, when we talk about only NAND gate, then it means also sum of product. NAND gate. Why? The easiest scenario, think about a single term. A single term. Okay, single term. For example, A, B, C. This is y equals A, B, C. How we will implement it? AND gate directly, right? This is y, A, B, C. Now, if I have a bubble over there, it's still a sum of product, right? Because I have a single term, and that term has a product in it and inside it. If I have a sum between them, then that is product of sum. In this way, I could flip this bubble using De Morgan theorem, right? And we could switch this AND into OR, and then it will be product of sums, right? So we could have NOR gate out of that as well. Again, as I said, you don't really need to remember these things. If you look at the equation, by now you should be really able to differentiate between sum of products and products of sum. We always assume by default that we want to represent anything, even if I ask you to simplify a Boolean equation, by default, it should be leading into sum of product, okay? This is our default, and this is what we like because it comes natural with the algebra equation, okay? Now let's see another example. When I implement this, is this sum of product? First, when I look at the terms, what are the terms? Here it's easy for you because there are parentheses, right? So how many terms do we have? 3, 2, 1. So we have 2 terms. Excellent. This is 1. And this is another, right? Because there are parentheses, right? How many literals? 3, or 3 variables, right? Okay. Now, can we use something similar to this? Of course. Yeah, you can start drawing by that. But remember, this is not sum of products. This is product of sums. Each term has a summation inside it. There is no sum between 2 terms, right? There is a product between the terms. And that's telling us that we should have here something followed by something else. What should we have over here? OR gates. Excellent. So here should be OR gates. Here should be AND gates. Okay? And then you could implement whatever it says over there. For example, A NOT. So you would go with A bar and then B bar. You connect them to OR gate. Let's in fact do it. I think it's better to erase it. Keep the things at the top. Is Andrew here? Not yet. All right. Remember, we have 3 inputs, so we'd keep the same thing for each input. Do we have? We ask ourselves before we draw it. Do we have nuts? Yes, we have 3 nuts over there. So that's why we need the 3 nuts. If we don't have nuts in the equation, no need to draw those nuts. Okay. This is fake premium. All right, now the first term, we would use green color, for example, would go with the first one. Remember, we said this is product of sums, so we need to build the sums first. This is OR, right? Now, what are the input for the OR? We have A bar first, so we'd connect from here, a wire, and then B bar is here, so we just take solid bubble, then we connect it over there. Done with the first term. Now, where's the second term? Is this guy between the parentheses. So when I assume 3 input gate is allowed, and then AB, so we go with the blues, this first one, and then B, second one, and then the third one is C NOT. And then Since this is product of sum, so we need to multiply these together. Remember, this always should be 90 degrees vertical wires. So take vertical and then vertical again, or 90 degrees, 90 degrees, and this is the output as y. This is how we implement this equation. Okay? You could ask yourself after you are done, are we using all NOT gates? If we are not using any of them, you could also delete it because you are requiring extra gates for nothing. So here we are using A bar, we are using B bar, we are using C bar, done. So this is perfect, right? Yes. Sorry? No. You can remove the wire, yeah, but not the C, because C we need it for C bar. The wire is always the cheapest element in the circuit. You could add as many as you want. The only thing, it might affect the resistance. But normally this wire very thin, so you don't increase the resistance, okay? So you could delete the blue one, but it's really not impacting. What we're worried about is the gates itself. The gate is something huge. For example, this is not, is 2 transistors. So it's taking space, okay? Plus taking power, taking energy, and so on. All right? So this is what we have. Now you could optionally go with this shape. I don't recommend it. So it's better to keep it all in horizontal sign. And if I ask you to name this, you could name it yourself. You could easily here add a notation to the circuit. Okay? Okay. A funny topic called bubble pushing. Bubble pushing. And this is heavily relying on De Morgan theorem. Heavily relying on De Morgan theorem. Let's see an example. So here, how to implement this into a circuit. Any volunteer? I want to implement the first one into a circuit. Yes, please, Alex. Sorry? Yes, please. Yeah. Which color? So we have A, B, all with the nut. Excellent. We have multiplication between A and B, so we need AND first. And there is a nut at the top, which means the output is inverted. Excellent. Now I want you to convert it using OR. We don't want the AND. We want an OR. Remember, if we want to convert AND to OR 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 to AND, directly De Morgan theorem. Directly. De Morgan theorem. Excellent. So where are the two sides? De Morgan always asks you, where are the two sides? Deciding where are the two sides is the most important thing. Excellent. You split A and B. Now what we do? Between them, there is a sign. What is it? Excellent. And then we flip it into add sign. Excellent. And now what we do with the bar? We distribute it over the two sides that we decided in advance. So now we converted the AND into OR. Now we just need to implement that. Excellent. You added the bubbles. Why you add them? Excellent. Because we are not using A and B. We are using A bar and B bar. And then there is an OR. So if you are running out of AND gates and you left with only OR gates, you still can convert your circuit to use OR gates instead of AND gates, right? Excellent. Thank you so much, Alex. And this is what we call And this is what we call as a bubble pushing. Bubble pushing. Because we are pushing this bubble to go to the input. Okay? You cannot simply just move that bubble to the input. You really need to do something with the gate itself before you push the bubble. And that to satisfy the De Morgan theorem. So if I ask you to push those bubbles, don't just simply move this bubble from here to the input. That's wrong. You really need to go through this. You decide where are the two sides in my equation. Remember, if there are parentheses, then each parenthesis term is really a single term. That's one side. You cannot split it half. You take it as one side, everything else is another side, and then you flip the sign from multiplication to or from or to multiplication, and then you distribute the bar at the top over the two sides that you decided. Not over the variables, but over the two sides. If this has a C multiplied with B, so this bar will be over B and C together. Okay, and then you continue until you get no more large bar at the top of the variables. Let's go with the second one. Any volunteer want to implement this equation as a circuit? Any volunteer? Come in. You really need to break that barrier in order to practice these things. Which color?
It will be De Morgan.
Yes. Always bubble pushing is De Morgan. Sure if the people online can see it. So we have A plus B all to the bar. Excellent. You split it into two sides, and you flip the sign. You distributed the bar over the two sides. Excellent. No, done. You're done.
Oh.
Now you need to draw it. You need to design the circuit. No, wait a minute. Which equation are you implementing? Second one. Do we have or? We don't have or. So and is like half circle. Excellent. Excellent. You're adding nuts. No, the nuts should be coming from the wire, connected to the wire.
That was supposed to be the wire.
No, the wire of B. Connect the input of the nut to the wire of B. So you should all the time have single input as B. You cannot have two Bs. So one B, you have a wire, take a wire from the wire, and then create your own nut. No, the nut should be flipped vertically. Same as you draw it first time. Excellent. Excellent, yes. Now you have single A, single B. You cannot have two A's. That will make things more complex, right? Because you need to switch two switches all the time. When you change A, you enable two, which doesn't make sense because for sure you'll forget one of them. All right? Now wire from the output of the nut. No, wait a minute. Make all the time vertical wire from the output of the nut. Vertical wire. And try to not cross the nuts. Leave the nuts, leave some space, go a little bit down, and then take from the wire itself another vertical. No, this one, keep it. Keep going with the wire. Yeah. Yes, same thing with the other nuts. Okay, yeah. All right, let's see. We take from nuts. You go over there. Excellent. Now we could add optionally a dot at the nuts, a dot at the wire of the nut at the bottom. Yeah, excellent. And the other one. No, the input to the AND. Yes, excellent. Now this way, you are sure that they are connected over there. And we have an AND, we have a nuts over there. Excellent. It's all perfect. Now remember, this drawing, when we have a single gate or two gates, you could really use your classmate method. So you could directly go with something similar to this. When we have more complex circuit, you could go with this structure. Okay? For this one is single gate, you could directly say A and B and take two nuts. But that's excellent. Yeah, thank you so much. I appreciate it. Right? And this is what we call as a bubble pushing. You can see whenever we have the bubble at the output, we just take it to the input, and then we can go ahead with that. So this topic is a bit tricky because it doesn't come directly, and I ask you, can you change the AND into OR, for example? I don't do that. I don't ask you, can you push the bubble? I don't do that. Normally, what we ask, like, you have this many AND gates, this many of NOT gates, use them. Good luck. Now, if you look here, how many NOT gate do we need? Here. 1. Over here. 2, right? And that's the first thing to decide. If I ask you, you have only a single NOT gate to implement this equation. You look here, oh, come on. This need really 2 NOT gate. How would I implement it using single NOT? Right? And that's the thing you should deal with. How you push the bubble from the output to the input or from the input to the output. Remember, you need to satisfy De Morgan theorem. It's extremely easy. The only trick in De Morgan is how you decide where are the two sides of the equation. You need to split your equation to two sides, and then everything's straightforward. Okay? Now, we could call this as a backward pushing, and this is forward pushing, but this is nothing to remember. It's not important. Okay? Any question so far? We're going to move to extremely important topic after this. Okay? Hopefully it's clear to all of you how you move from an equation into a circuit that can be implemented. All right, here's the fun part. So now we are going to study a new method on how you can simplify any Boolean algebra equation without using all the theorem that we studied so far. Okay? This is a method can replace all the previous ones, but not all the time. Not all the time. That's why we teach both methods in order to simplify the equation. We will see where this method will fall, okay, and where it's really succeed. What do we call this method? Karnaugh maps. Okay, Karnaugh maps. Why we call it this way? The guy who invented the method. When it was invented? 1953. So you can imagine 1953, a method that's still valid until today. And there is even a large number of research papers on improving this paper. So this is a real paper published in 1953 by a single author who was working at Bell Labs. And that time, I think he was 32, 34 years old, I guess. Okay? He was born, I think, 1920s. And then until that time, I think 31, 32 years old. What's his name? Maurice Karnaugh. Okay? Could be a Russian name. I know Russians are extremely good in math. Extremely good in math. Okay? And surprisingly, he lived for 98 years old. And he just passed away about 4 years ago, or 3 years. Okay? Now, what is this method about? Before jumping into that, this is just a reminder. We are going to use this a lot in this topic. Please remember the essence of sum of product, product of sum. Hopefully by now you know how to build the truth table, because that's the first thing that you need to do for Karnaugh map, is to build the truth table. You need to build the entire truth table and then you move ahead from there. So for the input, we have no issues so far. So I already teach you a method that there is no doubt about it, okay? Hopefully no confusion, no mistake, no error. Automatically just propagate everything. Now with the output, it really depends on the equation that you have. For those min terms, again, there is a method that I already teach you how to fill all those terms over there, right? There's another method how you fill all those terms over there. So you just propagate the input, whatever the input you have. Remember, the max term, min term does not depend on the output. It only depends on the input. So we cannot have here E as one of the variables in any of those terms. All we have is only the input. We have C and M. If we have X and Y, then we should have X and Y over there, okay? If this is sum of product, then the terms should be products in there, right? We shouldn't have addition in those terms. So in each of those terms, we should have a product sign. And then whenever we have 0, 0, then there is a not. Whenever we have a 0, not. Whenever we have a 0 over here, not over there. As simple as that. Now the sum of the product of sum is the opposite. When we have ones, we should have a not. So 1, 1, not, 1, 0, not, nothing. When we have a 1, not. When we don't have a 1, then nothing. Okay? As simple as that. Do you understand this? Hopefully, no confusion so far. All right, let's move to Karnaugh map. Now, I won't ask you in this question to build the truth table, but this is really the first step that you should do, okay? Normally, we ask you a descriptive question, meaning that I ask you something similar to that student who went to the restaurant. Do you remember the picture we generate from Gemini? With the student who wouldn't eat if the restaurant is not clean or if they cook some specific meal, okay? Normally, those what we have as a question, right? Ask a descriptive question, and your goal is to translate it into a truth table. How many input we have? We put it in one side, and the output in another side, okay? And we need to build the complete thing, the whole thing, until we arrive to 1, 1, 1 in the last line. That's the first step, okay? Now the second step, how many input do we have? We have 3 inputs. We have 3 inputs. Now, we need to build a new table. And this is what we call as a Karnaugh map, okay? Now, since we have 3, we always split them into 2 and 1. 2 variables and 1, okay? All the time. Since they are 2 and 1, then how large this table should be? So for 2 variables, how many permutation can we build? 4, excellent. Then that is for one side. And now since we have another variable, and that variable can be 0 or 1, then it should be 2 options for 1 variable, 4 options for 2 variables, and that is 2 times 4 will give you 8 different permutation, okay? So our table should be, since we are splitting the input into 2, what we call them A, B, C, so we split into A, B in one side, and the third one in another side. And remember, this order is extremely important. We don't say C here and A, B over there, okay? So A, B, the first 2 variables in this side, the third variable in another side, okay? How many permutation for those 2 variables? We said 4, right? So we need to split this into 4 boxes. Now, since we have another variable that could take 2 options, either 0 or 1, then we need to duplicate that. Okay, now we have 8 permutations. What should be in there? What should be in here, in here, in here? Now first, let's go with those 2 variables. What are the permutations that we can build for any 2 variables? If you get confused, always build a truth table of 2 variables. We said always start from right side, alternate between 0 and 1, right? The other variable alternate with 2 zeros, 2 1s, right? Now these are the 4 permutations that we could have. For Karnaugh map, we said, let's use another color. The first option, we should go with the first entry. So 0, 0. The second one with the second cell. The third one, where should we place it? To the last cell. To the last cell. And then 1, 1 to the third cell. Why do we do that? Excellent. How do you know that? Excellent. Did you read the book? I was hoping that you say yes. I was hoping that you say yes. Yeah, please study the book. Before you come to class, please study it. That's excellent point. So all the time we change from one box to another, only single variable. Only single variable. From here to here, where are the variables that we changed? We changed B, right? It was 0, we changed it into 1. How about here? We changed the first one. A was 0, now it's become 1. How about here? We changed B. It was 1, we went for 0. Not yet, don't stop. How about? What do we change from here to here? A. So we have 1, now it becomes 0. So you see now we connect the entire thing by a single move, by just alternate or swap these 2 things, right? Now it doesn't matter where you start, you connect already this one with this one, okay? And we will see why we do that. This is extremely important. How about the C? Over here, single variable, doesn't matter. So all the time it will be single value changing, right? So what should be the value here? 0, and here 1. This is the second step. So the first step, build the truth table, the entire thing. Second step, build the Karnaugh map based on this schematic. So you go with the first permutation, second permutation, last permutation, and then third permutation. Likewise, in here, if you have 2 variables, so if it is 2 by 2 or 4 input, then you split them into 2 and 2. Over here, exact same story. First permutation, second permutation, last permutation, and then third permutation. Okay? And then, easy for you to fill the truth table over here. How? Let's see. When C was 0, and A and B are zeros, what is the value of the output? Let's see, 0, 0, 0. The value of the output is 1, right? Which is the first line in the truth table. This guy. When C is 0, A and B are 0, 0. What is the output? Is 1. So we have 1 over here. When C is 1, A, B are 0, 0. When C is 1, A, B, 0, 0, what is the output? 1. When C is 0, 0, 1, when C is 0, A, B is 0, 1, don't get confused, don't swap the values, right? 0, 0, 1, what is the value of the output? 0. And then you will see the pattern yourself that we are going really in order. So we go with the first, second, third, fourth, which is 0, without even checking those values, right? Over here, there's a trick, because this is the last one. So we go here. So this is 1, first row in truth table, second row, third, fourth, maybe I can annotate it. This is 1, 2, 3, 4, 5, 6, 7, 8. This is how it goes. If you check the C's, A, and B's, you will see this is the order that we are going. 1, 2, 3, 4, 5, 6, 7, 8. So we have 1, 1, 0, 0, and then 0, 0. What do we have in 7 and 8? Someone else? Don't stay silent. 0, 0, which is the last 2 rows, right? 0, 0. Excellent, Alex. All right. Yes.
That approach would be in the first
Where?
column.
Where? Here?
Yeah, yeah. So
It cannot be another row. Should be multiple of 2. We are going into the power of 2. So if it should be more rows, then it should be 2 variables over here. And that will give us 4 permutations. So we'll go with 0, 0 here, 0, 1, 1, 1, 1, 0.
Yeah.
Yes.
So when that happens, you fill it by column the same way?
Yes,
Okay.
exactly same thing. Same order. And you can think about it because this is 0, 0, and this is 0, 0. So that will be first one. Now this is 0, 1, but this is still 0, 0, right? So you go with the second row in the table. But here, we don't go with the third. We go with the same approach over here. We skip that row. We go to the last row, and that will be third cell. And then the fourth will be the one before. So we'll go 1, 2, 3, 4, 5, 6, 7, 8. Right? Let's do it, maybe. I have an example on that, but maybe let's do it. Please ask question. All of those are really great questions. So let's build a Karnaugh map for 4 inputs. 4 inputs. Can you give me 4 variables? Anything? Name them. Name them.
B bar, B bar.
No, as a variable, literal. What do you want to call them? X, Y, Z, W, anything? S, T, U, V? Okay. S, T, U, V. Okay. Now, what are the first ones? Those 2. Those are the second ones. Okay. So now, want to build this huge Karnaugh map. Please remember how we draw it. We had this line over here, and then we said these first ones will go here, ST, and the others will go here. Remember to keep the exact same order so we can match it with the truth table. Then it's easy for us to fill this from the truth table. If you do any mistake here, if you swap them, then it's still correct, but you really need to go line by line and try to figure out where's the value. Now, we split this into 4 because we have 2 variables. They got 4 permutations, so we need 4 boxes. Now, likewise in here, we have 2 variables, 4 permutations, so we need to split it into 4 boxes. All right? Now, let's annotate it. We said we go with 0, 0, right? 0, 1, and then 1, 1, and then 1, 0. If you ever forget, ask yourself how we could move from one box to another box with only one move. And a move here means changing only 1 bit value. They're not allowed to change 2 bit values. Any box to another box, change only 1 bit value. So 0, 0 to 0, 1, we are changing only this guy into 1. Likewise in here, 0, 1 into 1, 1, it means we change only this one into 1. Likewise in here, 1, 0, we change only the 1 into 0. And keep going to this one. 1, 0 to 0, 0, we are changing this bit value into 0. So all the time we change only one bit value. Yes, please. No, you should do it this way. It will be easier for you to fill directly from the truth table without checking the values, without checking even what are the input values. Okay? Please always do it this way. It will be extremely straightforward for you to get the truth table out there. Now in here, same story. 0, 0 for this cell. Here, can someone tell me? 0, 1, excellent. 1, 1, excellent. 1, 0. Okay? Exact same story as in here. We are only allowed to change one bit at the time. Now, what will be the order if we look at the truth table? And that you'll see it nicely over here. This is the first row in the truth table. Second row, third row, fourth row. Okay? Fifth row, sixth, seventh, eighth. An exact same story. Now remember here 1, 1. So you need to skip to this column. We have 8 and then 9, 10. Remember, jump here, 11, 12. Now over here. 13, 14, 15, 16. And yeah, when we have 4 input variables, we will build 16 row in the truth table. Now, if you ever get confused about this, just go back to the truth table, say, where do we have U and V as 0, 1, and ST as 0, 0, and then get the value from there. But it will be really easy for you to imagine this numbering, and then it will be directly, without even checking the input, you go directly over the truth table. What's the first row, second row, third, fourth? Keep going. I know it's a bit difficult. That's why I call this lecture as Introduction to Karnaugh Map. We don't expect to finish the entire topic today. We will continue next lecture on too many examples on Karnaugh Map. Okay? But hopefully by now you remember the structure, how we build it. Yes, please. Same story. Don't get confused by those numbers. The rule is you change one input at the time and then move ahead from there. Don't focus on this side, focus only on the top, and then move from here to here. How you change one value? As simple as that. You can imagine this is with 0, 0, 0, 0. Same thing, right? And then you keep moving from there. Maybe you can do it at home and show it next lecture. All right? Yes, please.
Is there a benefit to ordering by changing from the value?
Of course, and we will see that. I have one example for you. That's an excellent question, but I don't think we will cover it today. But we will see it next lecture for sure. There is an extremely benefit by allowing this to correlate with the first one. If we don't do this single bit change at the time, we will not be able to consider this and that. We will see how we will consider them. Okay? All right, assume we build this Karnaugh map. Then what's next? Where is the simplification? Where's the equation that we will get? Now, it's telling you, look at your Karnaugh map. You need to pair or group the ones. You need to group the ones. Look at the ones. You have ones and zeros, right? Look at the ones only. How many ones do we have in the map? 2, 1. 1 and 2, right? Look at them and try to group them. Try to group them. What does it mean? Now you allow to group single 1 or 2 1s together or 4 1s together, 8 1s together, and move on. 16 and so on. Okay? You're not allowed to go with 3. You're not allowed to go with 5. You're not allowed to go with 6, 7, right? Only you're allowed to go with the power of 2. So we have 2 1s. Can we group them with 1, each one individually? We could do that. Can we group them as 2 1s? We could do that, right? These are possible options. Can we group them with 4? No, they are only 2. Now, Karnaugh, in his paper, he said always go with the maximum number, with the maximum group size, okay, with the largest group size. So we said we are allowed to use 1, we are allowed to use 2. What is the biggest group?
2.
Group of 2 items rather than single item. Then we will go with 2 together. Then he said group these together as one group. As simple as that. And then what is my equation? Is that a group? This group represents the simplified equation of this problem. How we would get the equation? Excellent. So by default, we look at sum of products all the time. And here we want to build sum of products for this group. Now, we would look at the inputs. Whenever we have a 0, it means a nut. You remember? I give you this recall just before we start. Whenever we have a 0 at the output, right, we just go with nuts over there based on the input. When we have 0 over here, we go with nut, nut. When we have 0, 1, then it means nut without nut, right? And likewise in here. Hopefully they can follow online. All right, let's look at the first item. What is it? So this is 0, 0, and 0, right? Remember, this is the first variable, second, and then third. Now, the first variable, is it 0 or 1? Here, look here. All in the K map. Don't ever look at this. Done. We build this, and this will be by itself full representation. This is 0, right? What we said right now, when we have the input as 0, then it's a nut. Excellent. Then A is a nut. Where is the second variable? Is it 0 or 1? 0. Then remember, this is sum of product. So the terms should be multiplied inside, right? So we are trying to build the first term now. We have 2 terms because we have 2 1s in this group. So we're aiming to build something like that. A term with a sum inside because we have 2 1s. So 2 terms. Now with the first one, we are not done yet. So we build the 2 variables, but we have a third variable, right? What is the third variable? C bar, because it's 0. Now we are done with the first one in the group. Let's go with the other one in the group. So we are looking at the input in order. The first one is A. A is 0, it means A bar. Excellent. Second variable, B bar. Excellent. Third, C or C bar. Why? Excellent. Because it's 1, it's not 0, so we don't add nut. This is our equation. And then what's the output? You can just add it over here. That will be your equation. Okay? Are we done? We are not done. Why? Excellent. We can simplify, but we really don't need to simplify here. we can do a trick before even getting the equation. What is the trick? Now, this might be a bit more confusing for now. Maybe we can keep it until next time. But when we look at the vertical group, and we said it's equivalent to 1 in these two cases, then it really does not depend on the value of C. C is all, doesn't matter if it's 0 or 1, we still get 1. Then we really don't need to add C in the equation. This is a bit more detail, but we will go over it again in the next lecture. But remember this, when you build this equation and you see it vertical, then it means the equation does not really depend on that variable. And this is true. You can see it here. If the variable is 0 or 1, the output is still 1. It means we don't care about the third variable. So just remove it from the equation. Don't add it from the beginning. And that will be the most simplified equation. Now, if you look at the equation, oh, it looks like a bar b bar plus a bar b bar, then it's directly a bar b bar. This is your equation. And you will see this next time. When you look at this vertical bar, just look at those two variables, and that's it. That will be your equation. Don't try to add two terms together. Yes, please. Excellent. And that's the first point I told you. Sometimes we cannot replace everything we studied so far. It's not like this is going to replace those Boolean theorems and stuff like that, because sometimes you will end up with something that is nearly simplified, but is not the most simplified equation. And you might still need to apply some theorem over here to simplify it. Yes?
So that means
no, it's complete. It's complete and guaranteed to give you this simplified most of the time, but in sometimes it failed to provide the most simplified, but will give you nearly simplified. So it's way easier to start from here rather than starting from something else. And we will see a lot of examples where this could be very efficient in solving them. But remember, it all comes with trade-off. So we cannot say this is better because there is a complexity happening. You need to build a truth table first. You need to build the K-map, right? And then you need to group them. And then you need to extract the equation. And at each step of those, you could make mistakes. If you make a mistake, it will propagate. You will have a wrong answer at the end. Over there, in simplifying, you could go from one theorem to another, just maybe in 4 steps, you're done, right? Especially if you practice it well and you know the tricks, what you are looking for, which terms to consider together, and all those questions. Over here, it's systematic. You don't need to think about it twice. Just go step by step. You don't need to check theorem and all these stuff. But if you make a mistake, it's done. It will be wrong at the end. Okay? So it's up to you. If you have mindset that's good with systematic approach, I know where to go, step 1, step 2, 3, 4. Go with this method. If you are good in handling this theorem and think about it twice, then go with the first method. And that will motivate us why we have these two methods. One of you asked me last time, why we study this complex thing if there is an easy way? An easy way, it's not necessarily easy, but rather it's straightforward. It's guaranteed to work if you get the steps correct. Okay? This is what we mean by an easy step. You don't need to think about it. All right. Hopefully that was a nice introduction to the topic. We will continue next lecture with Karnaugh map. We will practice a lot. We will try to build as many maps as we can. And then that will be the end of the chapter 2. We will move to another important topic related to the processor itself and the DRAM. Any questions so far? All right. By that, we are near the completion of chapter 2, and that will be directly the project assignment number 2. I'm going to give you a truth table, and you need to convert to an equation that will be processed in the CPU. Okay? So you'll build a program that takes as input a truth table. It's up to you how you handle it. Remember, the first assignment was converting decimal into binary. So please leverage that. You could ask the user to insert each row as a decimal value, and then you convert into binary, or handle it whatever way you would wish. And then you would convert it into sum of product based on the ones and zero at the last column. But remember, if the zero are less than the ones, then it's not wise choice to go with sum of product. Okay? So you would watch the number of output. Do we have zeros more or ones more? And based on that, you would decide whether you go with sum of product or product of sum. And then you would get an equation out of that. I'm not sure if I will ask you to build a K-map. By the way, this we can call it in short as K-map. Okay? It's Karnaugh map, but in short as K-map. I'm not sure if I'm going to ask you to build the K-map, but it will be fun. Remember, it's allowed to use GenAI. It's up to you. You can use whatever you want, but don't copy the answer. Don't copy a code. And we can easily check that. And this is why we are taking a bit of time. We are checking those things. Okay? I might ask you to build the K-map over there. It will be nice practice to see it in programming, how it works. How many of you want that as an assignment? Project assignment. It's not in class. 1, 2, 3, 4, 5, 6, 7, 8. Oh, Eden wants it. Okay. How many of you doesn't want to have K-map in the project assignment? And then the rest? Okay, the rest are fine with either, right? Okay, so let's have it. I will add it to the project assignment. I will give you enough time, probably 2 weeks, to implement it and have something working. By the end of the day, your output should be an equation. And by next topics, we will see how the processor is going to process those equations. So it's really those project assignments are built on top of each other. And every time we are building our processor gradually as we have in real life. Okay? Thank you so much for today. I'll see you on Wednesday. Thank you, guys.